So I'm working on this hardware-only I2C protocol designed for a AS5600 magnetic rotary encoder. And when we left off, I created this receiver protocol, which does an acknowledge bit every 9 clock pulses. And using this circuit, I was able to make that happen. Now it's time to test it out to see if it actually will receive data from the I2C. So I'm going to enter the data for the initialization here manually, and let's see what happens. Zoom out. 0, 1, 1, 0, 1, 1, 0, 0. Acknowledge. Raw angle sensor. Acknowledge. Repeat start. 0, 1, 1, 0, 1, 1, 0, 1. Acknowledge. Now, in order to start the data transfer, I'm going to press this switch right here. The switch starts the counter for the I2C receiver. Zoom in on it a lot. And let's go. And there's data coming in. And it should change based on the magnetic sensing here. Let's see how I could do this. Yep, you see it changing, the character of the data. Okay, if I can stop it, show you the data bytes coming in. Restart it. And you can see here the SCL line, which is the yellow tracing of the serial clock. SDA line is blue, that's the data line. And it's running at 5.87 kilohertz right there. Which means that if I'm getting 12 bits out of this, which is 2 bytes at a time, so it has to go through 2 8-bit cycles plus 2 acknowledge bits, so 18 total clock pulses. So that's this divided by 18, which is over 300 hertz. So 300 times a second, I'm getting a refreshed 12-bit reading. And that's all with the manual receiver circuit based off of a CD 4106 clock, a CD 4017 timer, and an op amp, and a bunch of little side components. And that's our I2C protocol hacked by hand, designed for the AS5600. But it really can be utilized with any I2C device. So this is just an illustration, but it works. And now to stop it, all I'm going to do is just turn off this switch. That stops the counter. So now let's see if we could put this all together. Here's the initialization schematic for the initialization circuit that I made in the previous video. And here's the I2C receiver circuit. And so now we just need some glue logic with a handful of components to put it all together. So basically I have the outputs of those going together. The output of the master counter turns off the initialization signal so it doesn't interfere with the receiver circuit. And let's put it all together. So to test this out, I have the I2C receiver on the left and the initialization circuit on the right. And these are all tied together as per the schematic I just had up. And let's see how it works. So I have the SCL tracing in yellow and the SDA tracing in blue, and on immediate power up, it does a start condition from the master counter. And after the start condition, it enters the address of the I2C device, which is the AS5600, and that's 0110110, and then it writes to it, so it's a 0 bit at the end. Then there's an acknowledge done by the device that lets you know that it's communicating with it. And then we're writing to the raw angle sensor, which is 00001100, and another acknowledge. And then there's another repeat start condition here that you can see. And after the repeat start condition, you now re-enter the address of the I2C device, only this time with a 1 at the end. And there's the acknowledge bit, and that reads from the raw angle sensor address. I set up an LED here to let me know when it's done with the initialization. And now I just have to press a switch in order to turn on the receiver circuit in order to start clocking in the data. And here with the button pushed, you can see the data coming in. Let me zoom in on it here. And you can see the data coming in from the device. This is 12 bits of data, 1 high byte of 4 bits and 1 low byte of 8 bits. And right now it's cycling through. It's just showing the data from the last time the magnet was put to the device. So now we're going to test it out to see if the data pattern changes when you apply the diametric magnet to it. And you can see as I rotate it around, you can see the data bits changing periodically. I'm going to demonstrate that better in a second. Here it is in close-up, and you can always see the 4 low bits of the high byte, followed by the acknowledge and another low byte and another acknowledge bit. And that repeats over and over and over again every 18 clock pulses. So this is the data, and I'm going to unpause it, and here it's running freely. So now when I put the magnet on the AS5600, you can see the data pattern changing. Here's a low one you can sort of see, but it just keeps on going as long as the circuit is on. And now just to turn it off, you just have to stop the counter. And with that switch, I'm going to stop the counter now. And that's it, no more data. So now in order to display the data, I've come up with this circuit here that uses 2 74HC 595 shift registers and a divide by 2 clock circuit using a D flip-flop. And basically, we take the pre-inverter SDA signal, which is an upgoing pulse every 9 clock cycles, and put that through a CD4013 D flip-flop configured as a divide by 2 clock. And then we shorten the pulse using a high-pass filter, a capacitor, and resistor to ground. Then we take that signal and put it through a diode to get rid of the negative going voltages. And it forms this nice voltage spike that's short. And let's test this out. Divide by 2 D flip-flop. It's a CD4013, and it's basically set in toggle mode where the Q bar is connected to the data, so it toggles back and forth every time there's a clock trigger. And so I have it being triggered by the main clock, or the main data line, the acknowledge part. So that's going to be my latching signal, and I have it going to shorten. The way I have it going to a 27 nanofarad capacitor and a 2.2K resistor to ground, and then a diode to get rid of the negative voltages coming out of there. And I have this very short, tiny peak signal. And now we just have to turn it into a 5-volt pulse. So it's pretty synchronized though on every clock cycle. So every other clock cycle there's a latching signal. So that should latch every 18 clock pulses from the main SCL line. So now we'll put this signal through an op-amp configured as a comparator in order to turn it into a short pulse that comes once every 2 acknowledge cycles. And that will be our latch bit, or our latch pulse for our circuit. To test this, I took away the I2C device, the AS5600, and instead attached just a regular SDA line, which stays high and then goes low for the acknowledge bit every 9th clock cycle. And then here is the pulse coming up every 2 acknowledge bits to latch in the data. And I configured it in this way so that the width of the pulse is about the width of the acknowledge bit, so that the data is latched on the second acknowledge bit once both bytes are delivered to the shift registers. And to display the data, I'm going to have the SDA line be the data line for the shift registers, and the SCL line being the shift register clock, and the latch bit, which we created just a second ago, will latch in the data when every 2 bytes of data are delivered to the shift registers. So to test this out, I have a setup where I put 8 LED lights for the first 8 bits and the oscilloscope probe to the 9th bit, which should be low because this is the acknowledge bit, and it should stay low alongside, and I have this alongside the SDA line oscilloscope probe in blue. And let's see what it looks like. So you could see that the SDA line is acting appropriately. The 9th bit, which is the acknowledge bit, always stays low. So this is what the timing is supposed to look like with the SCL line, SDA line, and the latch line. And if the timing is right, all the bits should correspond to what's labeled here. Now I'm going to attach 16 LED lights to the appropriate outputs of the shift registers in order to visualize the data without the oscilloscope. There it is running the display. There's the data coming in here. You can see with the magnet adjustment. Now, as I put the magnet on the AS5600 and rotate it in various directions, you could see the 12-bit value of the angle change as I rotate the magnet according to the angle of the magnet. And as you can see, the timing here is correct because the acknowledge bit, the 9th bit, is always staying low. And this is working well. But now let's test to see if it correlates with the data the way it looks on the oscilloscope. And so right now I have the oscilloscope on alongside with the LED display. And the best place to test it is at the transition point from 0 to 360 degrees and vice versa. And as I move the magnet or rotate the magnet around, you can see it goes from extremely high bit value to a low bit value. So I'm gonna put in a freeze frame here for a very high bit. As you can see, 4 pulses low and 4 pulses high, and here's a very low bit where the high bits are completely low and the LEDs are off, and so that correlates very well. So now we no longer need the oscilloscope to display the data, and in fact we no longer need the LEDs since this is working correctly. And here I'm testing it at the 0 to 360 degree crossover of the magnet, and you can see it goes low then high. And so the output of this will be fed to the location, a binary counter, or an address value of a memory chip. So this is working as expected. As always, thank you for watching, and I'm going to leave you with the schematic.